In this video, I'm going to walk you through the post lab for Lab 1, Enthalpy of Solution. First question on the post lab contains all of the data that you collected in the experiment. First of all, the mass of the sample, you recorded that in part 2, and then also the final and initial temperatures of the solution you recorded in part 4. The rest of this is going to be stuff that you have to calculate or answer based off of your data. The first thing that we're going to do here is calculate the change in temperature for your solution. Remember to calculate the change in temperature or the change in anything. We want to take the final and from that subtract the initial. I'm just going to put some random data down here. This is going to be data that is absolutely nothing like what you'll be working with in the experiment. So let's say that my sample is 100 grams. That's nowhere near what you had in this experiment. And let's say that my initial temperature was 50 degrees Celsius and my final temperature was 0 degrees Celsius. So using that information, we're going to calculate the change in temperature, final minus initial. Remember, we definitely want to be paying attention to whether this is going to be a negative number or a positive number. So we're starting with 0 degrees, that's our final temperature, minus 50 degrees, that's our initial temperature. This has a change in temperature of negative 50 degrees Celsius. That negative sign is really important. It's letting us know that the solution is getting colder. Now you're going to answer the question, if you were touching this reaction while it was taking place, would it feel as though it is getting warmer or getting colder? So you want to think about the temperature that it started with and then the temperature that it went to over the course of the reaction. What would that feel like to you going from 50 to 0 degrees Celsius? That would definitely feel like it is cooling down or getting colder. Then you want to answer the question, is the reaction exothermic or endothermic? Exothermic means that heat is coming out of the reaction, exo for exit, and endothermic, into, that means that heat is going into the experiment. If heat is going out of the experiment, that would mean that it is going to feel hot when you touch it. If heat is going into the experiment, that means that it's going to feel cold as you touch it. And the reason for that is because the heat that's going into the experiment is being taken from your hand or whatever part of your body you're using to touch. So since this reaction feels colder, that would mean that it is an endothermic reaction. And you're just going to do the same thing for your other two samples right here. Then you're going to move on to the next question. And this has to do with calculating the moles of each one of these substances that you worked with. So first thing that you're going to do here is take the mass of the sample from your first data table and you're going to copy it down into the mass of sample box in data table number 2. So this number is just going to be the same thing as this number. You're also going to either calculate or look up the molecular mass for each one of these compounds. Now that means that we're just adding up the mass of the sodium, the nitrogen, and the 3 oxygen atoms. If you don't feel like doing that, remember you can always use the internet. We're looking for the molar mass of NaNO3. And that is 85 grams per mole, 85 grams per mole. And then we want to, I guess I was wrong. You can't necessarily look all of them up on the internet because you do need to show your work down here for how you actually can calculate the molecular mass of NaNO3, but looking it up on the internet is going to, help you make sure it's like checking your work down here. So show your work for adding that up. And that would just simply mean, like, let's just say that we were doing this for CH4. That would mean that we would say 12 for the carbon atom and 4 times 1 for the hydrogen atoms. That would be 16 grams per mole, something along those lines. Obviously not with this because this molecule is not one of the ones that we're working with in this experiment. And then we're going to use this information, use the molar mass and the mass of the sample to calculate the moles of the sample. So the way that we go about doing that is begin by writing the mass of the sample. And it's going to be helpful if we write not just the unit, but also the molecule, the molecular formula. And then we want to multiply it by a conversion factor that has grams on the bottom and moles of NaNO3 on the top. And we're going to fill this conversion factor in with our molecular mass, which says that 85 grams is 1 mole. The grams of NaNO3 cancel out the way that we have this set up. We just do the math on this. 100 divided by 85 is 1.176 moles. And again, these numbers, my molecular mass is correct, but these numbers are definitely nothing like what you're going to expect to see when you do the experiment yourself. So then we are going to move on to the next data table, and some of this is going to be information that we have copied from data tables number 1 and 2. So first of all, the delta T, the change in temperature, that is going to be what we calculated right here. I'm just going to copy it and paste it over here. So here's my delta T right there. And then also the moles of the sample, that's what we just calculated. So I'm going to go get that number, and I'm going to take my moles of my sample, copy that, and paste that over here. Now for the rest of this table, it is telling us that we are going to be calculating Q. Q is the symbol for heat, using this equation right here. Q is calculated by taking C, the constant heat capacity, which is given to us right here, and multiplying it by the change in temperature. So down here is where we're going to show our work for that. Q equals C delta T. C is the constant 418.4 joules per degrees Celsius, and then we want to multiply that by our delta T, negative 50 degrees Celsius. The degrees Celsius is going to cancel, and we're going to be left with units of joules. 418.4 times negative 50. Remember, these numbers are nothing like what you're going to get. Definitely want to pay attention to the sign of Q. Don't lose any negative signs. So I'm getting negative 20,920 joules. Then for the next box, we're just going to simply convert our heat from units of joules to units of kilojoules. And we're going to do that, show our work for that in the space down here. So to do that, I'm going to take my joules, negative 20920 joules. I want to multiply by a conversion factor that lets me cancel out joules and convert into kilojoules. Kilo is the prefix for 10 to the third. That means 1 kilo is 10 to the third joules. My joules cancel out. All I'm doing here is dividing by 1,000, and that's going to be negative 20 point, I'm just going to take it down to 3 sig figs, 20.9. Now for the last spot here, we're going to calculate the heat one more time. This time, look at the units. It's going to be kilojoules per mole. So in this spot down here, we're going to do that work. Kilojoules per mole. This is going to be as simple as taking our kilojoules and dividing it by our moles. So for this, we want to take our kilojoules and divide it by our moles. Our kilojoules, which is, again, don't lose your negative signs, 20.9. Oh, I just realized that I wrote joule instead of kilojoule. 20.9 kilojoules divided by 1.176 moles, and that's going to give me 1.176 negative 17.8 kilojoules per mole. So these are, again, saying it like I think this is the fourth time, these numbers are very different from what you will expect for your own data for NaNO3, because I just made these numbers up, not based on anything normal. Also, these are 3 very different compounds, so don't necessarily expect to get the same or similar values of Q out here on the end. You could end up with 3 very different numbers out here, and that's perfectly fine. The only thing that you can do to kind of check your work is that if you have like a negative delta T, you should be ending up with a negative Q out here. If this is positive, you should be ending up with a positive, and you should be able to see a little bit of correlation between the magnitude of the delta T and the magnitude of the Q as well. But other than that, these calculations are all pretty straightforward.